Okay. See, vapor pressure can be given as the pressure exerted by molecules of vapor on the surface of liquid when both are in equilibrium with each other. Okay. See, this process is called evaporation, and this is condensation. Okay. Now, let us see the factors that influence vapor pressure. You know, vapor pressure depends on the nature of liquid as well as on temperature. Okay. Coming to this nature of liquid, there are two different types of liquids: more volatile than less volatile, more evaporating, less evaporating. Let me give you an example. See, supposing if water is taken in one hand and ether is taken in the other hand. Ether being more volatile evaporates readily. Okay. Whereas water, which is less volatile, does not evaporate that readily. Okay. The point is, this is more volatile and this is less volatile. Okay. But why? What is the reason behind this? Why is ether more volatile whereas water is less volatile? Volatility, as I said, it actually depends on intermolecular attraction. Volatility can be given as inversely proportional to intermolecular attraction. Let me tell you. See, if suppose there are lesser intermolecular attractions, like we discussed yesterday, this molecule, if suppose the intermolecular attractions are less, can overcome the attractions readily and can easily come up to the surface. Not only comes up to the surface, but also escapes into space above the liquid. So, lesser the intermolecular attractions, greater is the volatility. because it can easily overcome the attraction by making use of less amount of energy. It can actually overcome the attraction. Whereas suppose the intermolecular attractions are more. In that case, overcoming the attractions becomes difficult. For that, the molecule has to use more and more amount of energy. As a result, it becomes difficult for that molecule to come up to the surface and also to get escaped into the space above the liquid. So it is this, right? If the intermolecular attractions are more, I mean, when competition is more, I can say volatility will be less. Okay, and vice versa. Now, we can actually give the relation this way. Finally, vapor pressure is directly proportional to volatility. More volatile, more vapor pressure. More volatile, more is the vapor formed. Okay, and more is the vapor pressure. But remember, vapor pressure. Okay, let me take some more space here. But for now, you remember these two things. Vapor pressure and volatility are directly proportional. Volatility and intermolecular attractions are inversely proportional. Now, let me tell you an important point. Rate of evaporation depends on surface area, but vapor pressure is independent of surface area. A very important point. Remember, evaporation. Yes, of course, if you have greater surface area, you'll have more number of molecules escaping into space above the liquid in unit time. But vapor pressure is different. Vapor pressure is the pressure exerted when the evaporation process has attained a state of equilibrium. Okay, so once the liquid and vapor are in equilibrium, the pressure exerted by the molecules of vapor on the surface of the liquid is vapor pressure. So this actually is independent of surface area, considered only when the two are in equilibrium with each other. Okay, so if suppose we consider water in a beaker and water in, say, a water body like a pond, sea, ocean, evaporation, I mean, rate of evaporation will be different in these two cases. Okay, depends on the surface area. Greater the surface area, greater is greater the surface area, greater is the rate of evaporation. But in these two cases, if you observe vapor pressure, it will be the same, because once the equilibrium is established, then only we consider the vapor pressure. So the time taken for the establishment of equilibrium will be different in different cases. Therefore, remember vapor pressure is independent of surface area, but rate of evaporation depends on the surface area. Now, let us see the effect of temperature. See, when vapor pressure and temperature are considered, vapor pressure increases with increase in temperature. But this is not linear. It's not linear, but exponential. So when a graph is plotted between vapor pressure and temperature, we get this type of curve. It is not this. I mean, it is not linear. It is exponential. Remember, vapor pressure increases with increase in temperature until the boiling point of liquid is reached. Okay, look at this. So this is the temperature at which the vapor pressure of liquid becomes equal to atmospheric pressure. Now the temperature at which vapor pressure becomes equal to atmospheric pressure is called boiling point of the liquid. As such, vapor pressure increases with increase in temperature. I can say till the critical temperature of the liquid is reached, because above critical temperature, liquid does not exist. Okay. Yes. Now the effect of temperature on vapor pressure was mathematically given by Clausius-Clapeyron in the form of Clausius-Clapeyron equation. Let's see that. Look at P is equal to beta into e power minus delta hv by RT. In this, so this is vapor pressure, beta is a constant, delta hv is a molar enthalpy of vaporization. R is of course gas constant, and this T is temperature, right? Now taking log on both sides, ln refers to log E, which you normally use in mathematics, but I'll be using ln for log base E, I mean natural logarithm. Ln T is equal to log beta minus delta hv by RT. Okay. Now this can of course be converted into base 10. 2.303 log. So this ln, I've written it as log. When I write log, it refers to log 10, and this refers to E. Okay. So 2.303 log P is equal to 2.303 log beta minus delta hv by RT. Dividing by log P. Sorry, dividing by 2.303, we get log P is equal to log beta minus delta hv by 2.303 R. Let me take it this way, 1 by. Now, this is Y is equal to mx plus c, right? Log P is taken on y-axis, 1 by t on x-axis. Then y-intercept is a log beta, and the remaining thing, of course, is the slope. A straight line with a negative slope is what we get when log P is plotted against 1 by t. Now in this case, this of course is log beta. Okay. Then slope is minus delta hv by 2.303 R. All right. Now, let me take that relation under two different conditions. Log P2 is equal to log beta minus delta hv by 2.303 R into 1 by T2. So P2 at T2 temperature. Similarly, log P1 is equal to log beta minus delta hv by 2.303 R into 1 by T1. So here it is P1 at T1, right? Now, now this can be taken as log P2 minus log P1. is equal to delta HV by 2.303 R into, say this is 1 by T1 minus 1 by T2, right? Now, this is a Clausius-Clapeyron equation. Okay. So this is about the effect of temperature on vapor pressure. Now let us see some more interesting points. Coming to the relation between vapor pressure and the boiling point. See, I told you very clearly that boiling point is the temperature at which vapor pressure of a liquid becomes equal to atmospheric pressure. Now let us take two different cases. Case one. Now let me just give an imaginary thing. Suppose this is vapor pressure. This is where the vapor pressure is. If it is to be taken to this level where you got atmospheric pressure, let me just say that the vapor pressure is very less. So in order to equalize that to atmospheric pressure, you know the temperature needed will be more. Okay. At the same time, look at this point. Supposing if the vapor pressure is say more, and if suppose it can be made equal to atmospheric pressure easily, if it is more, then you know the temperature needed will be less. Lesser the vapor pressure, greater is the temperature needed to equalize the vapor pressure to atmospheric pressure. Similarly, greater the vapor pressure, lesser is the temperature needed to equalize. So from this I can simply say that the vapor pressure and boiling point are inversely proportional. When this also is an important point. Lesser the vapor pressure, greater is the boiling point and vice versa. Okay. Now let us consider another important point. The relation between boiling point and the atmospheric pressure or say external pressure. Now, I have three interesting cases in this. In general, if we consider the boiling point of water, say at 1 atmosphere pressure, I mean the atmospheric pressure, it is 100 degrees centigrade, right? Now, when the same thing is considered, say, in a pressure cooker, let me tell you one very interesting point. You know, pressure cooker reduces cooking time. But why? See, it is because inside the cooker, the pressure will be more. Pressure goes on increasing. See, when pressure is more, now let me just give you an imaginary picture. This is where the vapor pressure of liquid is. See, under normal conditions, if this is what it has to reach, if you consider more pressure, I mean here because the pressure inside the cooker is more, the temperature required to reach the boiling point, I mean reach the atmospheric pressure, which has now become more, it will be little more than what it is earlier. Now the pressure is more. It can be atmospheric pressure, or you can say the simple pressure or the external pressure. Now, to reach this, if the temperature needed is this, to reach this, because see, apparently now the pressure is increased, not the exact pressure, apparent pressure we can say. Now, because it has increased, the temperature needed became more. Just an imaginary thing, just to make you understand the concept easily. Because when pressure is increased inside the pressure cooker, you know, boiling point also increases. Boiling point of water also increases. So within the pressure cooker, let me tell you that the pressure inside the cooker is more. See, when this pressure increases, boiling point of water is elevated. Now it will no longer be 100 degrees centigrade. It will be more than 100 degrees centigrade. Now see, suppose at 100 degrees centigrade, it takes say a half an hour time for cooking at a temperature more than 100 degrees centigrade. No doubt it takes lesser time than this half an hour, right? And moreover, there is one more interesting point. If the same thing is carried out in, say, an open vessel, if cooking is carried out in an open vessel, you know, you'll just be heating it. You'll be giving it heat. But the point is, water can boil only up to 100 degrees centigrade. Once the temperature of water reaches 100 degrees centigrade, even if you give it heat, it will be wasted because it cannot boil to a temperature more than 100. Whereas in the pressure cooker, the scenario is different. It just goes on taking whatever heat that you give. So this is the interesting point. Goes on taking heat, takes on heat, goes on building up pressure. As a result, even the boiling point goes on getting elevated. So that is about the pressure cooker principle. Actually reduces cooking time because in this, the boiling point is more than 100. Can go beyond 100 because inside the pressure cooker, you got more pressure, as a result of which the boiling point goes on increasing. So let me just tell you one point, that boiling point is directly proportional to atmospheric pressure, or you can say external pressure. Okay. As the pressure builds up, boiling point goes on increasing, and even heat is not wasted. Okay. So this is very important. Your heat is wasted because it cannot go beyond 100. But here heat is not wasted. That is how you can save fuel also using a pressure cooker.